All right. Tests are not graded. They'll be graded by next week. We are moving on to the new unit. I've kind of rearranged the order of things based on our new unit guide from College Board. So we're going to move into what's called simple harmonic motion now. I think it'll make more sense, make it easier for y'all to learn. Simple harmonic motion.
Are you wanting to record this?
I did record it. Yeah, thank you for reminding me. You musicians in here, harmonic, yes, harmonics in music. This is where that word, or the same usage of the word. However, we'll be describing different types of vibrations. So simple harmonic motion, the gist of it, the definition, is repeated or oscillatory, which just means back and forth, up, down, left, right, A, B, B, A. Repeated or oscillatory motion that obeys Hooke's law, which obviously we'll describe. So anytime you see something moving back and forth, vibrating back and forth, moving back and forth, and it doesn't have to obey Hooke's law. If it doesn't, it's not simple harmonic motion.
So there's little door stoppers on the bottom.
Yeah. Yep. That will obey Hooke's law for a short time, but then energy will be dissipated and it'll stop. But yes. So obeys Hooke's law. What is Hooke's law? Let's define that. Or let's talk about what it talks about before we actually write the equation for it. Hooke's law describes forces that, and I'm going to personify the word, the forces here, that want, they obviously don't want to, they just naturally do so, but they want to return objects or systems of objects to a state of stable equilibrium. This might sound strange and complicated and weird, but I'll obviously elaborate on this. First of all, what's stable equilibrium? If I took like a half pipe and I rolled a ball down it, eventually the ball would come to a rest at the bottom, right? After friction and air resistance took its energy away, and it would end up being there. And if I took that object, if I pushed on that thing to the side and I remove my finger, it's going to go back. It's eventually going to get back to the same spot. That's stable equilibrium. If I was very talented, which I'm not, I could take that same ball and perfectly balance it on the top of a hill, right? A very smooth hill. And I could get it to stay there. But if I gently nudge it, then it's going to roll off the side and it won't return to its original position. This would be unstable equilibrium. It's like the most basic types, but yeah. In the future, you STEM majors will talk about stable versus unstable equilibrium all the time. There's these things called Lagrange points around any object that orbits another object. And some of them are stable, some are unstable. And so if we take a satellite and put it in a stable Lagrange point, then the satellite will like migrate around the center there, but it will stay there. We don't put satellites in unstable Lagrange points because they wouldn't stay there. They would be stable for a minute, but then they just end up rolling down the hill. Right? Okay, so Hooke's law describes forces that want, quotes, to return objects to a state of equilibrium. Some examples of that. And these are the examples that we will focus on in this class. Hooke's law, by the way, is very wide-reaching. There's applications of Hooke's law that go far beyond what we study in this class. If you take AP Physics C next year, then we'll elaborate on them quite a bit then. But at this point, we're going to study two basic types of motion. Simple harmonic motion, that's the motion of pendulums, okay? And the motions of, there it is. And the motions of masses hanging or being attached to springs. So the mass spring system is what we're going to focus on mostly, but here I got the mass spring system in a state of equilibrium, and it's stable because if I push on it, it goes back, right? If I lift it, it goes back. Now, if I push down and hold it, there's a net force that's pointing up. How do I know that? Well, when I let go, it accelerates upward, right? So I displace the object this way from its equilibrium position. The net force now points in the direction that wants to get the object back to its equilibrium position. It is kind of complicated here because I have an upward spring force and a upward force exerted by the spring and then a downward weight force. But as soon as it passes equilibrium, and the spring force obviously has to be bigger because the net force points up because it accelerates up. But as soon as it passes equilibrium, then the weight force is larger than the spring force, and so the net force now points downward. And so as it goes through, once it passes the equilibrium point, then the net force will point down, and again, Hooke's law will be obeyed. The net force will want to get the object back to that equilibrium position. Now, in an ideal case, it will never stop at the equilibrium position, because here, and we know this physics now, I do work in stretching the spring. I've now stored energy in the system, potential energy. When I let go, that potential energy gets converted to kinetic energy. When the object gets to the equilibrium position, all of the energy is kinetic, right? Because the spring isn't stretched from equilibrium anymore. So it's all kinetic, and so when it gets to equilibrium, it's going to keep moving through it because it's got kinetic energy at that point, at which point it's going to start gaining gravitational potential energy, right? And then it will come to a stop, zero kinetic energy, but the force wants to get it back to equilibrium, right? And so if I just let it go, then that just happens over and over and over and over again. If this was an ideal spring, same usage as like ideal gas or ideal pulley, then this motion would continue forever and it would never stop. Okay. If I put it in a vacuum chamber so there's no air resistance and I did that, it would never stop. It does stop though because there's what's called internal friction in the coils in the spring, and so that will actually dissipate energy in the form of heat over time, and it will come to a stop. In this case, here in the room, it stops mostly because of air resistance and that internal friction. Okay. But we focus on ideal springs because to talk about it'd be beyond the scope of this class. That's what professors say whenever they don't want to. Well, when it literally is beyond the scope, but that they don't want to talk about it because it'll take too much time, or they just don't know it that well, which is not the case with me if I ever say that. Okay, all right. So that's a mass spring oscillator. Pendulums are the same thing. This is the equilibrium position for the simple pendulum. A simple pendulum is simply a mass that we can consider to be a point mass, meaning it's pretty small, attached to a light spring. Light meaning we approximate the mass of the string as zero. It's inconsequential in relation to the mass of the actual ball at the end. And I displace the object from equilibrium. This is the equilibrium point. That's where it wants to be. If I displace it, then I have a tension force that's not going to do any work, but I have a weight force that has a component that wants to get the ball back to its equilibrium position. So I let it go. That force drives it back towards equilibrium. But as soon as it goes past that, the force redirects to try to get it back to the equilibrium position from this side. And so it just swings back and forth. We have the same energy interplay, kind of. I give it gravitational potential energy by pulling it to the side. Then the gravitational potential energy converts to kinetic. When it's at equilibrium, it has maximum kinetic energy, so it goes through and then converts that energy back to potential. And again, in an ideal scenario, with no loss of energy due to friction, no air resistance, the pendulum swings forever. Okay. These are the two cases that we discuss in this class, the two main types of simple harmonic motion that we study. There are more complicated types of simple harmonic motion. This is a physical pendulum. This is a much more useful pendulum. It's the same kind of thing, though, right? I displace the physical pendulum to the side and I let it go. Same interplay of energy and forces, same types of restoring forces as with the simple pendulum. This is how grandfather clocks work, right? When they construct grandfather clocks, they are pendulums that swing back and forth, and those pendulums are constructed so that they will swing back and forth in a certain amount of time, usually 1 second, so that's literally how they keep time. They calculate the period, what we'll call the period of a pendulum as it swings back and forth, and make sure that the pendulums that they create have a period of about 1 second. So that's a little more useful. There's something called a torsional pendulum. Oh, sorry. Those of you at home didn't see my physical pendulum. This is a physical pendulum. Torsional pendulum is like, I can do it with Wilbur, but I don't think, if I spin Wilbur this way, then he's going to eventually stop and spin back. Let me do it this. That's going to take too long. Wrong way. Wrong way. If I take my pendulum here, you might have done this with like yo-yos or on a swing. If you twist yourself up on a swing, you ever do that when you're a kid and you swing the other way? That is a torsional pendulum. So if I twist this guy one way, then he ends up going back the other way. And then he overshoots equilibrium. And then he goes back that way. And it oscillates back and forth. Right? I don't know if you guys remember me talking about a guy named Henry Cavendish who figured out what big G is, the universal gravitational constant. He was the very eccentric scientist from the 1800s that designed an experiment to actually determine the value of G by directly measuring gravitational forces between normal everyday objects, large lead spheres. He couldn't measure them directly, but he could set an apparatus in oscillation, and the apparatus that he set up was a torsional pendulum. And by calculating how frequently it went back and forth, and it was very slow. It was a very slow oscillation. By measuring that oscillation rate, he was able to determine the value for big G. Ingenious experiment. Yeah. So that's a torsional pendulum. Those two we actually study in AP Physics C, physical pendulums and torsional pendulums. So I'll see y'all. I'll see you then, Kyle. See you then. We will come back to this guy in a minute. There are a lot of other aspects, though. Anytime you see a spring and you have an oscillation, if you're in your car and your car bounces up and down, it's because it's bouncing on springs. That's what shocks are primarily composed of. I think they're more complicated nowadays, but in old school they were just springs. This is another thing that we do in Physics C, and I just want to bring it up because it's kind of fun. Where's my mouse go? Where's my mouse? If we were to dig a tunnel directly through the earth, all the way through it, to the other side, and then throw Kurt in it, just throw Kurt in the tunnel, then he would move just like, oh, there's clouds out in space, that's weird. He would move exactly like an object on the end of a spring oscillating up and down. Exactly. Hooke's law would describe this motion. The big kid version of Hooke's law. We don't do the big kid version of Hooke's law. We just do the one for mass on the end of a spring. The big kid version of Hooke's law is actually, as you'll see in Physics C, the first differential equation you'll ever learn if you take AP Physics C in high school. A differential equation is just a calculus equation involving derivatives.
If you hold out the Earth like that, would gravity work the same?
No. Yeah. It would not work nearly the same as it does when you're out here.
No, I'm saying, but would it work like that? Would it be like that?
Yeah, it would be exactly like this. Yeah. And if you want to know why on my YouTube channel, I have the video where I go over this.
It wouldn't be like, but the Earth couldn't be like that.
No.
Right? The pressure.
No.
Yeah.
The farthest we've ever dug down is like 8 miles. The radius of the Earth is over 6,000 miles.
Would it be messed up if you hollowed it out? Like, would it be
You take AP Physics C next year if you want to learn the answers to those
I'm
questions.
gone. I'm seeing.
We'll take calculus-based physics in college. Okay, so that's simple harmonic motion. That motion obeys a form of Hooke's law. Again, not the one that Wolf studied. Hooke's law is all the same, but we use a case of Hooke's law that's specific to mass on springs. But if you want to look it up, most of it's algebra. I think it might all be algebra. But we instead of Kurt in Physics C, we use Trenton Hunt as the example. And so the video is titled Pendulums and Throwing Trenton Down the Hole. It's on my YouTube channel. So if you want to see that, it's pretty cool. So we'll come back to that. I'm actually going to reference that in a little bit once we get the mathematical equation for Hooke's law, which we'll do now. So in words, this is what Hooke's law is all about, but there's an equation. Again, the big kid version will describe all simple harmonic motion, all types of simple harmonic oscillators. It is a differential equation, a calculus equation, that relates the displacement from equilibrium to the forces that then act on the objects. we're going to focus on mass spring systems. Mass spring systems. And we want to use Hooke's law to relate the spring force and the displacement. And we're going to talk about displacement in the x direction just to make it a little easier. Let me bring this up real quick. It'll be like this. So, you see that on the screen? Yeah. So if I hit play on the simulation, this guy's fixed. This is like the wall, the spring attached to this mass. This is the equilibrium position. If I displace this object, hold on. If I displace this object, I get a spring force. You guys see that spring force? I displace that object from equilibrium. We always measure our positions from equilibrium. So that would be our position vector x. And I then get a spring force that points towards the equilibrium position. Okay? What do you think happens to that spring force when I stretch the spring more? It definitely gets bigger. Very good. So now I've increased my displacement, and I get a much bigger force. Much larger spring force. Okay. What that means, and if I hit play, this thing oscillates back and forth, just like it was oscillating up and down when it was a vertical spring. I did turn friction off here, so this will literally go on forever. What this means is that the force is constantly changing. Newton's second law tells us that if the force is constantly changing, then the acceleration must be. What can I say about the acceleration if the force is always changing? What does Newton's law say about forces and acceleration? Guys, this is fundamental. You should know this now. This guy's mass doesn't change. So if the force changes, what does the acceleration have to be doing? It also has to be changing. Remember the kinematic equations? Also known as uniformly accelerated motion equations? You can't use the kinematic equations for simple harmonic motion. Some students end up trying to do that even after I've told them several times. You cannot use kinematics to describe this motion. You cannot. Because uniformly accelerated motions assume constant acceleration. So don't try it. Don't try it, can't do it. Okay. All right, that's an aside. Let's go back to trying to relate forces and displacements. And to do this, we're actually going to mathematically determine, or actually experimentally determine, the type of relationship that Hooke's law describes for a mass spring system. And to do that, I'm going to just do some basic science. Normally this would be a lab that you guys would do, but because can't do labs, we're going to, because we can't do labs, I'm just going to do it up here and show you. So what I want to do is relate the force and the displacement. This is what science is all about. Science is all about observing nature, observing one thing that may be affected by another thing, and then determining what that relationship is. And how do you describe those relationships? With the mathematics you guys have been learning for years, right? Sometimes it's linear relationships. Sometimes they're quadratic relationships. Sometimes they're like uniformly accelerated motion, right? Acceleration is proportional to the square of sorry, I don't want to get too much into that, but it's all about looking at two things, maybe more, but you want to focus on two because it's easier to do that way, and just seeing how varying one affects the other one, and then provide some mathematical framework for that. That's what physics is all about. So what I'm going to do is just displace this spring from equilibrium for various locations, measure the spring force, and after I do that, I'll put that on the graph and see if there's a relationship. If they're not related in any way, then we just get scattered dots everywhere and it doesn't make any sense. If it's a quadratic relationship, we should expect those points to do something like this. If it's an inverse relationship, which it probably won't be in this case, then it would have, that kind of a graph, right? So all that stuff. So we're going to go ahead and measure this. And we got to be careful here, though, because I can't measure the spring force. I'm going to pull the spring force down. I can't measure the spring force on my finger directly. So I got to use my knowledge of Newton's laws in order to make this determination. If I pull down on this spring, what's the net force on the spring right now? Kurt?
Yeah. Net force on
You're not paying attention, are you?
I'm sorry. I'll pay attention.
What's the net force on the spring?
It says it's point.
No, what's the net force on the spring?
Oh, it should be 0 right now.
0.
Yeah.
So if I pull down on the spring, this hook is pulling up on the spring with the same force. If the hook pulls up on the same on the spring with the same force that's pulling on my finger, then that means that the spring is pulling down on the hook with that same force by Newton's third law, action-reaction. So get that? You understand that? I pull down on the spring, the hook pulls up on the spring with the same force, but opposite direction, so that the object stays in equilibrium. It doesn't accelerate. Newton's first law. And then Newton's first law also says, well, if the hook is pulling up on the spring with a certain force, Newton's third law said, remember, hook pulls on spring, spring pulls on hook in the opposite direction. And so by measuring the force that's exerted on the force probe, the spring pulling down on the force probe, I'm measuring indirectly the force that's pulling up on my finger. Okay. So I'm going to displace the spring a certain distance 5 different times. You guys tell me what that spring force says so I can make sure that I'm looking at this. When you do this, I'm measuring from the equilibrium point. I got to measure from the edge of the spring and then just its displacement from equilibrium. So I'm gonna displace it 0 meters. So what's the spring force? 0. Oh, dang it. 0. Now I'm going to displace it 3 centimeters, otherwise known as 0.03 meters. And you guys tell me, it's going to bounce around, but just tell me about. It can be approximate. What do you get? What do you see up there?
No, it says about 2.7 something.
2.7?
Yeah.
No, 0.27.
Yeah, that's what I meant.
What is it?
0.25.
0.25? Okay, now I'm going to do 5 centimeters, otherwise known as 0.05 meters. What do I get?
0.43.
Point-
0.42.
0.42. Now I'm going to do 9 centimeters. What do I get?
0.66.
0.66. Oh. Okay, and then I'm going to do 12 centimeters. What do I get?
0.9. No, actually it's 0.88.
0.88? 0.88. Okay. Those of you, especially future engineering majors, computers are going to be a huge thing, huge thing. Knowing how to deal with spreadsheet software is essential. Excel is not easy, it's very powerful actually. Excel is good software. Google Sheets, yeah. But it's gotten better over the years, but I like the Microsoft Office Suite better. I think it's more powerful. But what I can do with some data points, I've done this before in this class, I can just put these on a graph. Okay. Whenever you'd use a spreadsheet, normally if you use a spreadsheet software, the left one goes on the x-axis, the right one goes on the y-axis. So whenever I can put this on a graph by going insert, a scatter plot. Ooh. What kind of relationship does it look like exists between the force and the displacement? Looks pretty linear, right? Now I wasn't being careful at all, so it's not going to be perfect, but that's pretty good. That's pretty close to being linear, right? If I had this is a pretty weak sauce spring. It's pretty easy to pull it, right? Some springs are much harder to pull. Your garage door springs, they're pretty stiff. The shocks on a car, pretty stiff springs. So if this was harder, if this was a stiffer spring, what would happen to this graph? It'd be steeper. Because if I had the same displacement, I'd get a much larger force. And so my data points would climb higher. and I get a steeper slope. So, as is the case, as we've seen with the Newton's law of universal gravitation, you note proportionalities. Newton's law of universal gravitation, gravitational force proportional to the product of the two masses, inversely proportional to the distance between them squared. And then you figure out the proportionality constant in order to formulate the equation. So what we notice here is that the spring force is directly proportional to the displacement. So it's linear. So all I need to do is get this slope, put it in this equation, and then I have my equation for Hooke's law for a mass spring system. Right? The steeper the slope, the stronger or the stiffer the spring is, the harder it is to extend or compress it. Okay? So because this slope literally characterizes the nature of the spring, this is a constant that we call the spring constant. Okay? So the slope here, we can determine the spring constant of any spring by doing this experiment and determining what that slope is. So that slope is what's called the spring constant. And because spring constant starts with the letter K, it gets the symbol K in our equations. You did this in geometry, actually, when you did proportionalities. You learned X is directly proportional to Y and all that stuff. You usually use K as the proportionality constant. Well, we do that here. And so to turn this into an equation, it's not nearly as complicated as Newton's law of universal gravitation. It's just that.
Is this be F sub K or sub S?
Yes. And the force is a vector, and X is a vector. However, this is not entirely true. This is not true. I got to add something there to make it true. And to show you why, let me bring up this guy again. I'm going to take this spring, or this mass spring system, mass spring oscillator. This is equilibrium. I'm going to displace it this way. So I have a displacement this way, and I have a force this way. Now we're talking vectors here, so we're being very specific. Here I have a positive displacement in the positive direction. What can I say about the force?
The force is
It's in the negative direction. Mm-hmm. What if I have a negative displacement? Now I have a displacement that's in the negative direction from equilibrium. And the spring force is positive. Making sense of that is what lets you make sense of the concept of the restoring force. Positive displacement, negative force to get it back. Negative displacement, positive force to get it back. So I can fix our equation here just by throwing a negative in it. Right? I just throw a negative in front of that K. There we go. That's Hooke's law for a mass spring oscillator. On the formula sheet, it looks like this. That's what it looks like on your formula sheet. Absolute value in math means magnitude in physics, largely. So understand, though, that this is Hooke's law, but to really, truly understand the restoring force nature of Hooke's law, you want that negative there. If I have a positive displacement, I expect a negative force. So I have a negative times positive, giving me a negative force if I calculate it.
Wait, so where's the negative in the terms of the one on the formula sheet?
It's not there, but that's why the magnitudes are there. That's why you got to understand it at a fundamental level.
Gotcha.
If I have a negative displacement, then I expect a positive force. Well, if I calculate it, I got a negative times K times a negative displacement, giving me a positive force, which is what I expect. Okay. Make sense? All right. Now, I told you that you can't do, and I'll have a set of notes for this on Tuesday, by the way, like usual. Now, I told you that you can't use uniformly accelerated motion equations. You can't use the kinematic equations to describe the motion here And oh my gosh. And this will show you why. Because if I actually plot the motion graphs for an object that is accelerating, or the object that is undergoing simple harmonic motion, you know, if it was uniformly accelerated motion, the acceleration is a parabola, the velocity time graph is a linear, and the position versus time graph is a parabola, the velocity versus time graph is linear, the acceleration versus time graph is a horizontal line. If I wanted to plot the position, velocity, and acceleration graphs, position versus time, velocity versus time, acceleration versus time, for a simple harmonic oscillator, this is what I get. You cannot use uniformly accelerated motion equations. You cannot use the kinematic equations for this. Okay. What types of graphs are those? Sine and or cosine. Right. Notice that when I started, when I started, I pulled the mass to maximum negative displacement. Right, pull it to the left and let it go from rest. So I started with zero velocity. Because when you're at maximum displacement from equilibrium, you get the maximum force, I also get the maximum acceleration. It's counterintuitive. When the object is not moving, it has the maximum acceleration. And so when I hit play here and try to stop it when it reaches equilibrium, which is right about there, now I have zero spring force, which means zero acceleration, but maximum velocity, because now it's moving fast as it will at equilibrium. And so that's why my velocity versus time graph is now horizontal. It's reached the apex of that hill, because now it's moving at its fastest, its highest speed. The acceleration is essentially zero, and the position versus time graph is essentially right in the center of its overall shape. And then it starts moving the other direction. Now my velocities start decreasing because my acceleration is now negative, because my force is now in the negative direction. And right about there, oh, I stopped it a little too late. Right there, it comes to a stop. It's now maximum positive displacement, so maximum negative force, maximum negative acceleration, and then I am at my maximum position, maximum distance from equilibrium. Those of you who know calculus, this is a negative cosine graph. That's a positive sine graph. It's a positive cosine graph. Derivatives and integrals, right? So on the formula sheet, we'll talk about this next week. On the formula sheet, there is an equation for the position of a simple harmonic oscillator mass spring system, and it has a cosine in it. Okay, we'll talk about that more next week. But you want to be able to know this. There's very common questions for simple harmonic motions for mass spring systems. Where is the velocity the maximum? Where is it zero? Where is the acceleration maximum? Where is it zero? The maximum distance from equilibrium we call the amplitude. We'll talk about that more next week. Same amplitude as your sine and cosine graphs in pre-cal. All right. Cool beans? Just to show you this real quick. No, I'll hold off. I'm jumping the gun there. Okay. Oh, energy. Working energy is coming back. Coming back with a vengeance. Not that one. Okay, so here again we're at equilibrium. If I take that mass and I stretch it, I have done work. Right? You can't stretch that spring without doing work. Just like when I lift this weight, when I'm doing my curls, feel the burn. When I'm doing my curls, I'm doing work. Whenever I do work on a weight, I store gravitational potential energy in it. When I do work on a spring, stretching it or compressing it, I store potential energy in it, just like gravitational potential energy. Doesn't work the same way though. The equation's a little different. And then when I release it, that gravitational potential energy gets converted to kinetic energy, right? Right there, spring potential energy. So I do work to store spring potential energy, also known as elastic potential energy. I let it go. that spring potential energy turns into kinetic energy. Right here at equilibrium, no more spring energy because the spring is back to its equilibrium position. Now I have maximum kinetic energy. So if I do 10 joules of work to stretch it, then it has 10 joules of potential energy. I let it go. When it gets back to here, it has 10 joules of kinetic energy. That's why it didn't stop at equilibrium. Forces are restoring. They want to get it back. But once it gets back, it's got kinetic energy, so it keeps on going. And then it converts that kinetic energy back to elastic potential energy. And then it just goes back and forth, again, in perpetuity, if this was an ideal spring. Okay. So we have an equation for that, for spring potential energy. The equation for spring potential energy, and I'm going to put elastic, because more generally it's elastic potential energy. Potential energy, the general symbol is a capital U. Because this is spring potential energy, we put an S there. It could be a rubber band, it could be a bowstring, right? When you pull back a bowstring, you're storing elastic energy in the bow. Not only in the stretch of the string, but in the deformation of the bow itself, that stores. Right? Just like when I take this ruler and I displace it and I let go of it, right? Same principle as a bow. In fact, the most powerful bows are the ones, at least not the compound bows, the crazy complex ones that they got today, but like a long bow, right? When you stretch that thing, you're deforming the bow and you store a lot of potential energy in it. Again, but we focus on springs, but it's the same general idea. Spring potential energy is 1/2 times that spring constant that we derived using that simple experiment times the displacement squared. It's on the formula sheet. Notice it resembles the kinetic energy equation very closely. It's not an accident. It's because the derivation of this, using the big kid version of work, the big kid calculus version of work, we can actually determine the brute force determine that equation just like we do with kinetic energy, and we use the same techniques and we use the same types of equations, and so we get a very similar result. The only difference is that the physical quantities themselves are different. Those of you that know calculus, you see a squared there and a 2 down here. So it happens when you integrate a linear function, right? Okay. Okay, so that's that. What that allows us to do now is deal with systems that have one additional type of mechanical energy. And I've set up a quick example of this up here. If you can't see, you can get to a place where you can. I have a cart with some mass on it attached to a spring on an incline. I do this. I've done work. I've stored some energy in the system. Now that I've stored too much energy in the system, I'm going to do work. I'll do work lifting it this way. And then it oscillates back and forth about the equilibrium position. However, because it's on an incline, its gravitational potential energy is changing. The spring stretch length is changing, and the kinetic energy is changing. So the full story here is initial gravitational plus initial kinetic plus initial spring equals final gravitational plus final kinetic plus final spring energy. Sometimes there's situations where you got to do that. More often than not, several of these, 2 or 3 of those will cancel out. They'll be 0, so you don't need to worry about it. All right. You guys pick up that little slip on your way in? Okay. Is that yours?
Is it?
Yeah.
Mine.
I think you're too focused on your phone there, Kurt.
No, I'm paying attention.
Okay. You weren't earlier.
That's true.
Okay. So let's go ahead and talk about some of the types of problems you can expect to see. An ideal spring hanging vertically stretches an additional 4 centimeters when a 2 kilogram mass is attached to the bottom of the spring and gently lowered to the new equilibrium position. Determine the spring constant for the spring. Okay, so an ideal spring hanging vertically, so it's just chilling, stretches an additional 4 centimeters when we hang the 2 kilogram mass from it. So initially the spring is just like this, and then I hang the mass from it and it stretches an additional 4 centimeters. So this is mass M. Its original equilibrium position was here. It is now stretched a certain distance x. This is how we determine spring constants of springs. It's relatively easy. Instead of me pulling it with my finger, I can actually do it more carefully by hanging a mass and letting it come to equilibrium, because then I'm not like, it's not relying on me holding it steady. Right? I can lower it to equilibrium and then just make my measurement there. It's actually more accurate to do it that way. And then I can just apply what I already know, Newton's laws. Right? At this point, if this guy's at equilibrium, it's not accelerating. So the downward weight force mg is equal to the upward spring force F sub s. And because I know it's not accelerating, those two forces have to equal each other. Now when you have a free body diagram like this, you don't need to worry about the whole negative aspect in Hooke's law. You know just by looking that the spring force points up and is positive, right, in our standard coordinate system. So all I need to do is, Newton's first law says that the spring force in this case equals the weight force mg. And Hooke's law tells us that the spring force, which we know is in this case is positive, is simply the product of the spring constant times x. And that equals the weight force. Divide both sides by the spring constant, or by the displacement x. And I get the spring constant is the weight divided by the displacement. We're going to approximate g as 10 so we can make this go a little quicker. Mass was 2 kilograms. G is 10 meters per second squared. X is 4 centimeters, which is 0.04 meters. That's 200 divided by 0.04. What's that?
Number.
500. What are the units for spring constant? Weight divided by distance. There's no special name for it. What's weight measured in? Who said kilograms?
Why is 2 times 10 200?
Oh.
You have it right though.
Okay, it's still right. Yeah. Good job. Okay, back to my previous question. Who said weight was in kilograms?
I thought you were just talking about what was the mass on the thing. I didn't hear you say weight.
Okay, what's mg measured in? Newtons. What is? I'm just giving you a hard time. What's distance measured in? Newtons per meter. That's the units of the spring constant, and it should make sense. For a given displacement, you get a given number of newtons of force, right? If it's 500 newtons per meter, how many newtons of force does the spring exert if I displace it 1 meter? 500 newtons. What if I displace it 2 meters? 1,000 newtons. Yeah. Get used to that kind of unit. That unit is what? Newtons per meter. Okay. Gravitational field strength, newtons per kilogram. Electric field strength, newtons per coulomb. This per that. If you understand it, it makes physics a lot easier to understand in a lot of cases. All right, that's number A. B. Well, now it says the spring is now placed. So we've taken that vertical spring and then we put it horizontal. Placed on a horizontal frictionless surface with one end fixed to the wall, as in the example on the simulation, and the other fastened to that same 2 kilogram mass. The 2 kilogram mass is pulled parallel to the spring, stretching the spring 0.1 meters. Calculate the amount of work required. Now, I could do it the fancy way, and I could measure the force as a function of distance as I pull the thing to the side by using a force probe, and then get that graph. And as we all know now, force versus displacement graphs, the area underneath represents the work. You'll also notice that the area under that graph represents the quantity, the spring potential energy, right? It gives you the same thing. So just like if I do 10 joules of work on the mass, it has 10 joules of potential energy. If I do 10 joules of work stretching a spring, there's now 10 joules of potential energy stored in the spring. So for that part, all I need to do is say 1/2 mv squared. 1/2 m. No. Guys, 1/2 kx squared. Come on. Come on, Tatum. 1/2 kx squared. And then I just, so that's the work. I should have written this. The work I do is equal to the potential energy that I will then store, which is equal to 1/2 kx squared. I think you need to turn your phone over. Which is equal to 1/2 times the spring constant. What's the spring constant? Oh, we did 500. Times our displacement,
Which is
0.1 squared.
Wait, is the spring constant still valid even though we were measuring in the
Yeah,
vertical
the
direction?
spring constant is a property of the spring regardless of its orientation.
Okay.
This is just one way to measure it. Yeah, and it's not something that we calculate like using theoretic. It's something that you just experimentally determine. And it's a measure. It's just a measure of the stiffness of the spring, essentially.
Gotcha.
And so that's 2.5. So I did 2.5 joules of work. And I'm just going to briefly talk about part C because it's a class about to end. Calculate the maximum speed of the mass. Well, what's nice about a horizontal spring system is that the mass does not move up and down, so we can ignore gravitational potential energy because it doesn't change. So we just have an initial spring potential energy, no kinetic energy, and we have a final kinetic energy, no spring potential energy, because at equilibrium is when it's moving the fastest, where there's no spring energy. So we set those equal to each other and solve just like we solved for conservation of energy for objects changing elevation and speed. Right. Okay. There we go. Hope you enjoyed it.
Is it bad that whenever I saw that I wanted to